Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 20th, 2025, about 2 days ago. The headline result is crisp. Core Attention Disaggregation lifts end-to-end training throughput by up to 1.35 times while removing data and pipeline stragglers. The paper is titled Efficient Long Context Language Model Training by Core Attention Disaggregation, and the implications for model training are quite significant. In short, this paper isolates core attention onto dedicated attention servers, uses a ping-pong overlap scheme, and scales to 512 H200 GPUs and 512,000 token contexts, with near-perfect compute and memory balance. Alright, Figure 1 shows why training stalls at long context. Core attention dominates work because its cost grows with sequence length, while other layers grow roughly linearly. This variance from document packing creates replica and pipeline stragglers that leave devices idle. Figure 2 presents the DistCA architecture, which routes core attention tasks to shared attention servers that dynamically rebatch shards. Table 1 explains why the split helps. Core attention holds zero model memory yet demands quadratic compute, whereas other parts scale with tokens. Alright, Figure 4 shows why variable length data chunks fail to fix long context imbalance. The left panel indicates memory usage spreads wider as the data parallel degree grows, which signals uneven activation pressure. The right panel shows attention compute divergence stays low for DistCA, but jumps above 50% for workload balance baselines at higher data parallel settings, so stragglers dominate. The takeaway is that moving sequences to equalize compute increases memory skew and still hurts throughput. So Table 2 summarizes the model setups evaluated, which matters because training speed and balance depend on width and head counts. The Llama 3.8b configuration uses 32 layers. Its hidden dimension is 4096. The per head size is 128. The larger Llama 34b variant scales depth to 48. It sets attention heads to 64 and adopts grouped query attention, which shares key and value across heads to reduce memory traffic. So Figure 10 shows consistent speedups under full four-dimensional parallelism, which splits training across data, model, pipeline, and context. In the top left panel, speed climbs toward about 1.3 times as nodes increase. The top right panel reaches roughly 1.35 times, indicating that longer runs see greater gains. For the larger model, the bottom panels show modest but steady gains up to about 1.25 times as input length grows. This pattern suggests that better load balance across pipeline stages drives throughput, because disaggregated attention soaks up idle time. Wrapping up, 2 takeaways stand out. Disaggregating core attention into a stateless service removes data and pipeline stragglers, and the DistCA runtime turns that into real gains, reaching roughly 1.35 times throughput at very long contexts. The broader implication is clear. Longer context training becomes practical and cheaper at scale. That is it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.